for coming to the talk. It's great to see there are many more people than I expected. So I'm going to talk about some work. So the slides that actually I'm using, they are not that new. Probably they're 1 or 2 years old. So maybe I should change the title a little bit. But it's still something interesting. It's definitely something I'm very excited about, and it's also something I hope to work on during the time that I'm here at Links at INRIA on the 4th and on the 5th floor. It's something I'm really excited about. So like Mark mentioned, I'm going to be here for 7 months until the end of July, and there are 2 research areas that I'm interested in. So one is wireless networks I'm going to talk about, and the other one is social networks. So that's another topic I'm really excited about. I think there's quite a bit of interest on the 2 floors in these topics. So I'm really looking forward to have some interactions on this discussion. So I have time. If you want to talk with me, I'm more than happy to meet. So let's see. So the title is a new perspective of distributed scheduling in multi-hop wireless networks. So what I would like to look at is wireless networks, kind of in the sense of a wireless ad hoc network. So the idea is we have nodes. Maybe they have some wireless transmitter and receivers, but they're they should be simple, okay? And they want to, or maybe on the fly, they want to create a wireless network and to use it to communicate, to exchange files or something like that. So this idea is not new, and it has been around for a very long time. So I think in 2000 it started a little bit, the research on wireless ad hoc network, where everybody was very excited about. And I call it a new perspective, so I want to highlight that a little bit. I think there has been a little bit kind of a understanding emerging, let's say, over 10 years of research in the field, let's say from 2000 to 2010, that kind of had the feeling when you look at scheduling algorithms in wireless networks, either you can get very good performance. So for example, if you use something like a max rate scheduling algorithm, you can get very good performance, but it's not easy. This cannot be easily implemented or cannot be implemented in a distributed fashion. Or you can have an algorithm that can be implemented in a distributed fashion, but then you sacrifice performance. But the idea is you cannot have everything, very good performance, and also a simple implementation. Okay, and there has been some work, I should mention that, so there has been recent work, maybe over the last year, over the last 2 years, that showed that this is not true. So there are random access protocols that we know right now that have a distributed implementation. There's throughput optimal and also the order delay optimal. Okay, so that's something new, and to me that's quite exciting. So it's something just from the performance of the type of protocols that we have. I think this really provides a little bit a new perspective. But it's also interesting a little bit more from a analytical, from a mathematical point of view. Often when people looked at random access protocols, in particular at the delay performance, what you looked at is kind of a steady state analysis. At the delay, you use the mixing time to characterize the delay. So how fast do you go to steady state? Or if you jump from one schedule to another schedule, how long does it take to visit the different schedules? Okay, so that was kind of the type of analysis. What comes out of the work that we have been doing, actually, there's maybe another way you should look at, and it's more on the transient behavior. Not how long does it take to jump from one schedule to the other schedule, but how long does it take you, let's say, from a random configuration to get to a tightly packed schedule. Okay, and these performances can be quite different. So it's also kind of what I think is interesting from a mathematical point of view, the tools that you want to use to actually study scheduling in wireless networks, in particular delay performance, maybe should be different than what we have been doing kind of typically. Okay, and another thing I feel that in the community, people said maybe around 2010, maybe even now, multi-hop wireless networks, it's not going to happen. It's just too complicated. It's not going to work. But my feeling is I'm intrigued by it, that maybe it's not true. Maybe we really can build this type of wireless, very dense or large-scale wireless networks. And it's also, I mean, this is a bit more theoretical, but I think from an application point of view, if we really could do that, to kind of think about what kind of application we could have, that also I think is interesting. Okay, so that's a little bit on a high level. I think the outline of the talk, first I'm going to talk about the motivation and give a summary of the results. Then I try to give some intuition behind the results, and then talk a little bit, not too much, but a bit more in details exactly what the results are. So we have two types of results, some analytical results for some particular models, but then also some numerical results for more general cases. And something I really would like to do is to extend kind of the analysis that we have here to the more general cases where you currently only have numerical results. It's not easy, at least to me it's not easy, but I find it quite fascinating, and I think it can be done, and then there will be some conclusions. Okay, so let's see. So this is a little bit the vision. I think it has been around in the community, in the networking community from 2000. It's the idea that we can build very cheaply wireless networks, kind of ad hoc networks that can be, a large scale. So we just drop some wireless nodes somewhere, we stick them on the wall or like that, and on the fly they're going to create a network. They start to talk with each other, exchange information, and we're going to have very good performance. Let's say like wired networks, there's going to be high throughput and high delay. And if I remember correctly, there was a lot of excitement around 2000, 2001, 2002. Everybody talked about wireless ad hoc network. There was a lot of funding, and there was a lot of excitement. And everybody felt, okay, it's just a question of time we're going to solve that problem. Okay, so you would like, around 2000 we knew a lot about wired networks, so it would be nice to have wireless network that just kind of the performance is very similar to wired network. But of course the problem is wireless networks are not wired networks, so you have to deal with the problem of interference. Okay, and there are different ways to model interference. So here that we do a little bit. So that's a wireless networks where the black dots, these are nodes, and these are wireless links between the communication links between the nodes. So it's a very simple view of looking at a wireless network. And the important thing is there's going to be interference between two links. So for example, if this link and this link is very close to each other, we assume everybody's on the same frequency, then they cannot transmit and receive at the same time, otherwise there will be interference. So we can have an interference graph that interference graph that characterizes which links can be transmitting at the same time. And if there's an edge between two links, it means they cannot transmit at the same time. So that's how we think about interference. It's a link interference graph. Which links can be active at the same time and which cannot be active at the same time. So it's a little bit the standard modeling assumption in wireless networks. Okay, and then the challenge is how to schedule packet transmission so that you respect this interference constraint. Okay, and the way you would like to do is ideally you would have to have a protocol that has a high throughput. Ideally it should be throughput optimal, kind of as good as any scheduling algorithm could do. It should have a low delay. Ideally optimal or order optimal delay. I'm going to be a bit more specific what I mean with order optimal delay. And also it should be simple, because we want a simple distributed implementation. So really we just can drop the nodes and it just works. It's nothing complicated. Okay, so that's what we would like to have. And then people say, okay, let's try to work towards that goal. And there were basically two directions trying to go to that goal. So one was a bit more from the theoretical side, to kind of to understand, okay, what is the best we can do? And that comes out from the work from max weight schedulers from Tasiulas and Efremidis, and it tells you, okay, what you kind of ideally what you would like to do. And if you do this, you get throughput optimal. What you get is throughput optimal, and it has a order optimal delay. Okay, so from a performance perspective, you get what you want. Okay, but if you want to implement it in a simple distributed way, it's not that simple. So kind of to find these max weight schedules, it requires, or it's NP hard. So it's a difficult problem. So the implementation, it's a little bit it's an issue. Okay. There's another approach, a little bit more from the practical side. We say, okay, let's start with something that we can implement. So you can look at CSMN, random access type of protocols, like Wi-Fi type of protocols. So by nature, they're designed so that they have a simple implementation. Okay. And what is not that obvious, but I think it took maybe 8 years of research, people were able to show, and that's already a little bit surprising, that these very simple protocols, they're throughput optimal. Okay, the throughput you get here is as good as in the best possible if you use a max weight scheduler. Okay, and said, okay, what about delay, and then there were some results that showed that the delay is can be very high. And then I think around 2008, maybe 2009, people really kind of tried to understand the delay and realized it's a very, very hard problem. Okay, and very good people worked on it and really tried hard. And then if you can't make progress, then you start to wonder, can this really be done? Okay, this goal of having a protocol that is simple, distributed, throughput optimal, and has very good delay, can this really be done? And then around 2010, there was an impossibility result by Shah, Tse, and Tsitsiklis that showed you cannot do that. Okay, there does not exist a protocol that both is distributed, has a high throughput, and a low delay. So it's not possible, and it's not possible for this interference graph that I just described. Okay. And then, so this is a little bit, I think that's is a little bit a downer, where it tells you, okay, maybe it cannot be done, okay? But there is a catch here, that this result here, it's for a very general case. So it's for all possible type of interference graphs, okay? And then the possibility is, and there is a hope, maybe there's a particular class of interference graph where actually you can do something, okay? And there are so Se Young is not here. I should mention, I mean, there has been now following up. Okay, all right, yeah, you see. So there has been, I mean, I think so we're going to look at one particular kind of way to get around this result. So Se Young had another way, and it's a very active area right now to try to get around that. So maybe the title should not be a new perspective. Yeah, it should be one of the new perspectives, because there are a couple of new perspectives. And it's also very interesting how now these different perspectives are emerging, and there should maybe be something more fundamental underlying, but this has not been discovered yet, at least not to my knowledge. Okay, so that's kind of what we say. Maybe there's a hope if you look at a very particular interference graph. Okay, and then the question is, if you look at the interference graph of a wireless network, it cannot be arbitrary. Okay, and in the sense by the law of physics, you interfere only with links that are close by. With a link that is very far away, I'm not going to interfere. Okay, I'm not going to interfere strongly with a link in Toronto, okay, or in a link in Montmartre, but I'm going to interfere maybe with links in that building. Okay, so this is something that we say, okay, it's not arbitrary, but interference is local. Okay, so you have a graph where links are local, or maybe one way to model is that you have the interference graph is a geometric graph where you kind of nodes are embedded, let's say, in the plane, and you only interfere with other links that are within a certain radius of you. Okay, so that's one way to think about kind of an interference graph for a wireless network. Okay, it's not a general one, but it's a very restricted one where only other links that are close to you in Euclidean distance you're going to interfere with. Okay, we say, okay, why don't we look at this? And then we saw there was no result, at least that we were aware of, that looked at this, that could say, okay, once you have like this geometric interference graph, that you can get all the three criteria, and that's what we will focus on. And also, so I was very interested in getting something more that can be implemented. So we started with random access, particularly with CSMA protocols. And it has been well known that classical CSMA doesn't give you all of it. It can have very terrible delay. Either you have very terrible delay or you sacrifice a lot of throughput. But you cannot have high throughput and low delay at the same time. And so I did that, I should mention, work with Madi, and he came up with an alternative to a CSMA protocol that seems to work, or at least that's very promising. Okay, so in terms of results, there are some analytical results where the interference graph is a very specific interference graph. Basically, it's captured by a grid or by a torus. And there, for this, Madi was able to show that with a small change to CSMA protocol, you get everything you want. Okay, you get throughput optimality, order, optimal delay, and it's a simple distributed implementation. Okay, and so this is for a very specific graph. Of course, I mean, wireless networks don't have this grid structure. So the question is, what about if you have kind of random geometric graph? Also what happens, let's say, if you, and that's in the end what you want to do, you put rate control on the top, so you also do some scheduling, some congestion control, what is happening there. And here we don't have analytical results yet, but we have numerical results that match, that show that the intuition you get here seems to carry over perfectly to this case. But there's no analysis yet. But I feel this is something that could be done, and it's something I would be excited, or I hope to work on, or at least the plan is to work on that problem. Okay. And so this is now a little bit a high level. So what is maybe a little bit the takeaway message? So one is that large-scale wireless networks that are simple to build and also have a very high performance. Maybe this is something that can be done. That's something that it's possible. So that's from a practical point of view. But also, and maybe I'm going to illustrate that hopefully a little bit in more detail. I think also if you're interested in mathematical modeling and analysis, I think there's a lot of interesting research in that area, because the tools that you have to use, it seems, is different than the classical tools. Okay. So this is a little bit the motivation and the summary of the results. And the next step would be to talk about the intuition. So why do we have problems with CSMA, and what's the trick to get around that? But maybe before I go there, if there are any, maybe I briefly pause in case there are any questions.
How do you quantify high performance? What do you call high performance?
Yeah, I'm going to make that a little bit more precise. Okay.
With respect to this Gupta and Kumar stuff, which is throughput varies 1 over square root of n.
No, it's not. It's not. It's a little bit different. I hope I'm going to make that a little bit more precise. But the idea is, I mean, there is a notion of a throughput optimality and a delay optimality that I haven't defined yet. And with respect to these two criteria, you would like to do as good as possible.
Peter, what is the demand model? Is it a general?
Oh no! So right now I'm going to go, but the demand model is going to be very simple. For the analysis, everything is uniform. But it's very simple. I mean, you're going to see. We just assume there's a fixed arrival rate within the capacity region, and we do analysis with that. I mean, the next thing would to have kind of like you always want to say, but you have to do some rate control. But we don't have flow level or anything like that. So it's still at a very early stage. So a lot of the things are very, very simple. Yeah?
Does all your links remain constant?
You mean the quality of the link?
Is the quality of the link?
Yeah, it's constant. No, there's no fading.
Okay.
So it's very simple, it's constant.
Okay.
Yeah.
I have a question concerning interference graph.
Yeah.
Does those kind of distributed nodes have to learn about the graph so as to optimize performance?
No. No. Other question? Okay, so maybe I go ahead, hopefully with the next, maybe also. So what's the intuition? So what we're going to look at is CSMA type of policy. So the idea is there's only one channel, and all the links use the same channel. And what you do in CSMA, so each link, you sense the channel. You see whether you already sense a signal or a transmission that's going on. Okay, and you sense until you detect that the channel has been idle for some time, let's say beta time units. And once you detect that it has been idle, you would start transmission with a fixed probability that can be dependent on the link. Okay, so with some probability you would start transmitting. Then let's say you transmit your packet, and after you finished, you go back to sensing. So that's kind of it's the CSMA. You sense, if you send it's idle. Here, with some probability, you start transmitting. When you're done, you're going back to sensing. So that's the protocol that we use. So here, you just have to listen. You don't have to know. And also, what we're going to assume that packets that take one time unit to transmit. Okay. When I talk about performance, sometimes I look at the throughput delay trade-off, and kind of the way I visualize it or kind of make the analogy is to an MM1 queue, and I hope I got that correct, that the expected delay in an MM1 queue with service rate mu and arrival rate lambda is 1 over mu minus lambda. Okay. Or you can say this is the service rate, maybe kind of the capacity of the queue. And if lambda, so mu minus lambda tells you kind of how close are you to the capacity of the queue, and then the delay is 1 over epsilon. Okay, so the idea is the closer you go to the maximal throughput or the capacity of the queue, your delay is going to go up, and the way it goes up, it's 1 over epsilon. Okay, so that's kind of to capture. If you want to have a very small epsilon, you have to tolerate a delay 1 over epsilon. Now you cannot do better than that. So that's the trade-off there. Okay. So this is the way we're going to think about it. So for the analysis, a lot of things are going to be very idealized. It's going to be a simple case, both in terms of the interference graph, but also in terms of CSMA. So something that we're going to do is an idealized CSMA where you can detect instantaneously whether the channel is idle. Okay. So the idea here, beta is 0. So immediately you detect that the channel is idle. Somehow you can do that. Physically, that's not possible, but it's a simplification. And then what you do is once you know the channel is idle, you start a timer, a distributed backoff, so exponentially distributed with this rate. And then when it has expired and it's still idle, then you would start transmitting. So it's a little bit the simpler version. Also, so it's an idealized CSMA. It's also in terms of the interference graph. We look at the grid type of interference and also a torus where we wrap around to avoid boundary effects. Okay, so it's a very stylized type of an intergraph. So also is that so these rates at which the links try to kind of the backoff parameter, the exponential backoff, we assume all links use the same backoff parameter. So it's something much simpler. So it's a uniform case where all the links have the same, we call that the transmission attempts, kind of this backoff rate. Okay. We also assume that packet transmissions are exponentially distributed, and we also assume there's single hop traffic. So even though it's multi-hop, it's single hop traffic. And when we talk about the delay or the queue, we assume that all the arrival rates are the same for all the links, and it's equal to lambda. Okay, so it's probably the simplest scenario you can think of and start with in order to try to get some insight. Does that make sense? Okay, and maybe something else. So it's an exponential parameter how long you wait until you try again. So if Z is very large, if the exponential has a very high rate, then you're very aggressive. You don't wait for a long time. And if Z is very small, then you wait for a long time. Okay. And so something we want to study a little bit as we change Z, how does that affect the performance? Okay. Yeah. Question.
I'm not sure if I got it right. So your transmission attempt probability is fixed, regardless of whether the transmitter detects that there's a collision or not.
So the trick is, maybe I don't want to go into the details, but if you can detect instantaneously whether somebody transmits or not, and if your timers are exponentially, you're never going to have a collision. Because with probability 0, 2 timers will expire at the same time. And if one timer expires just a little bit before the other timer, you will be able to detect it. And basically this is a trick I think that people have used right now in order to get around the collisions. So this is one trick not to have to deal with collisions. Another step will bring the collisions back in, as it can be done. But I think it's a valid way to start. But that's the reason. Yeah, there are not going to be no collisions. Yeah. Other questions? Okay, so it's a very simple scenario. About notation, so the service rate, how often the time average that the link is going to be scheduled, is going to depend on this rate here. Okay, so if the rate is 0, you wait for infinitely long until you make an attempt, so your arrival rate is going to be very low. Then you assume that you become more and more aggressive, you wait for a shorter and shorter amount of time until you try. More and more links are going to be scheduled, maybe the rate is going to go up. Okay, so here, how often you're going to be scheduled, it's going to depend on that attempt rate that you have. Okay, and also we have a uniform link arrival rate. So this here is from the MM1 model, that's the service rate of the link, and that's the link arrival rate. And the epsilon is going to be the mu of Z minus lambda, so that's a bit the connection. Okay. So let's see. So before we go into CSMA, let's try to figure out, okay, what's the best we could do? Okay, the optimal. Okay, and so in a grid interference graph, it's actually not hard to see that the maximal uniform link rates, it's a half. Okay, so packet transmission is one time unit. So the best thing you can do is in the grid is to switch between two schedules. So here it's the pink schedule and the black schedule. I mean, let's say if you have a centralized schedule, you would say all the black nodes transmit, then all the pink nodes transmit, and you switch between the two. And that will give you the optimal throughput. Okay, and you can think about it, you cannot do better than that. So the nice thing about this grid, it's very easy to characterize what's the optimal throughput that you can achieve. Okay, so that's the throughput. The other one is then the optimal delay trade-off. So we know that we have, we know the optimal, how you call it, throughput or service rate is a half. So epsilon is going to be a half minus lambda. That's kind of how close your arrival rate is to the maximal rate that you can support. Okay, and also what you can show here, if you would switch between the two, you would get an optimal throughput delay. It's 1 over epsilon of this order. Basically, looks like an MM1Q. So if you have MOSA, you couldn't do better than that. So the idea is you would have a centralized scheduler. You can really say you transmit and you transmit and you transmit. You would get very good performance, both in terms of throughput and in terms of the delay. Okay, but of course it's not distributed. You would have to have a centralized controller that does that. Okay, the question is now with CSMA, how close can we get to that? Okay, and so the next thing is to look at CSMA. So we're going to look, so this uniform, we're going to look at the idealized CMA with the uniform at trend rate. So the link service rate now depends on mu of Z. And something you can show that for large networks, as Z goes to infinity, as the nodes become more and more and more aggressive, you're actually going to, you're going to achieve the optimal throughput. Okay, and this is already, if you think about it, it's not that obvious. So basically, it tells you that CSMA is throughput optimal. Okay, and that it also tells you that CSMA samples the schedules with the right probability. So it spends 50% in the black schedule and 50% in the pink schedule. Okay, it does that, and it's not that obvious. Okay, and it's a bit of mystery. It's very nice that this is happening. Okay, so you have this sensing and all that, and really it samples its optimal as Z goes to infinity, and this is very nice. And say, wow, this is promising. And then the next question is, okay, we have good throughput performance. What about the delay? Okay, so the service rate. Okay, so here we look kind of how close the service rate is going to go to the optimal 0.5. Okay, and then so something that we have here is that if there's a threshold behavior. So if you're not too aggressive, if your tentroid is below some threshold here, then the delay that you're going to see grows logarithmic in the network size. Okay, and then there is another threshold. If you get too aggressive, it's above that. Then basically the delay goes up exponential in the network size. Okay, so so basically, so in order to get a high throughput, you have to be very aggressive. So your attempt rate has to be very high. But if then your attempt rate is very high, your delay really shoots up in terms of the network size. Okay, where L is the number of links. So it really goes exponentially in the number of links. So this tells you if you have a network with 10 links, your delay is already probably going to be quite terrible. Okay, and I think that's something that people really observed when they wanted to build this wireless network. If you had a few numbers of nodes, you wanted to go multi-hop. It just did not work. The delay was not very good. Yeah.
So here it's an asymptotic for fixed epsilon when L is large.
Okay. Yeah. So let me think.
Previously, you mentioned results for like when epsilon in terms of epsilon. So.
Yeah, so I think here is a fixed one, yeah, and it's just let me think about. No. Okay. All right. So very good. Okay. So here there's a coupling. Okay. So the epsilon depends on the attempt rate. You see, as I increase the attempt rate, this is going to get closer and closer to 0.5. But here it's kind of Yeah, so here it's not in terms of epsilon, but it's in terms of that attempt rate. But there is a coupling here.
Yeah, you mentioned like the best you can do is 1 over epsilon.
Yeah.
But here you're not seeing how does it behave.
Yeah, so this it's a little bit different here. Okay.
So you know how it behaves in terms of epsilon?
Let me think. So we come back to that. Okay, it's a good question. So we come back to that. But something maybe to point out here is, when you had 1 over epsilon, it does not depend on the network size. It's fixed on the network size. Okay, so here it depends on the network size. So that's what we want to highlight here. Okay, so if you have, let's say, a fixed epsilon, as you increase the network, it would go up. And so that's the point here a little bit, that the delay depends on the network size. And this is really that kills it. So if you want to build a large-scale network, I mean, it's not going to work. So that's the point here, that before it was 1 over epsilon, there was no network size. Here is the network size. And this is really what creates the problem. Does that make a little bit of sense? Okay. And this is, so this is this result that shows you if you want to have a high throughput, you're going to, for large networks, you're going to have a terrible delay. And here is an example. So we're going to look at the uniform arrival rate. We have the rho lambda over 0.5. And so here it's in terms of rho or epsilon is related to rho. And you can see once the kind of the attempt rate goes, or the load factor goes over 0.4, the delay starts to shoot up. So you see that threshold behavior. If your attempt rate becomes too high, suddenly the way the delay scales, it shoots up. And here is for different network sizes. This is for torus, for a 10 by 10, 20 by 20, and 40 by 40. And even if you fix, let's say, a load factor, for 10 by 10, it's here. For a 20 by 20, it's up here. And for a 40 by 40, it's up here. So even for a fixed load size here, as you increase the network size, the delay really shoots up very, very fast. And you could see if it goes to infinity, kind of if you have a very large network, you really have a wall here. Okay, you go to 0.4, and then the delay goes to infinity. Okay, and so this tells you if you want to use CSMA somehow, but this is for a grid. You have to sacrifice a bit of capacity. Okay, and then the question is, can you get around that? Does that make a little bit of sense? So that's the point here. Maybe that's a takeaway message here. If you use CSMA, it's throughput optimal in theory, okay? But in practice, your delay is going to be so high, you can't really use it. Okay, so once you have your throughput becomes too high, your delay just shoots up. Okay. Yeah.
Can you explain why that's 0.4?
I think you can, but it's not that trivial. So you have to do an analysis, and it comes out that there is this set 1 and this set 2 that you can characterize, and it's around here. I think, so it has been a while. I think even right now, it's not known whether set 1 is equal to set 2. I think there's a set 1 that has been shown, a set 2 that has been shown, but it hasn't been shown that they are the same. Okay, so here's an analysis, so it's around here, but it's, so these things are, I mean, you have to derive them, but at least to me, there's not a simple intuition that I can say because of this and this, it should be 0.4. Okay. And whether it's 0.4, it also depends on the interference graphs, or for a grid, maybe it's this. If you have something else, maybe it would be something different. Okay. Yeah?
So in your model, you wait like a backup, and when it expires, and you sense like idle, you transmit.
Yeah.
You become busy.
Exactly.
But you do so if you have a packet to transmit.
Yes, yeah.
If you have no packet, you don't do anything.
No, right now you always do. It's again a simple case. You always.
Even if you have no packet.
Exactly, yeah.
So if you have no packet, you keep the channel.
Yeah.
So will it change if you?
I think, I mean, it would, but it makes it harder, because right now we don't have to keep state information about this and that. If you want to go there, you have to take that into account. But it could change it. Yeah. Okay. So let's see. So this is so basically what we know is the optimal delay that we can count. It's 1 over epsilon. Another optimal delay, it's a delay that does not grow in the network size. Okay. And clearly CSMA is not order optimal because it depends on the network size. And then the question we ask, can we, with CSMA, can we get an order optimal delay, a delay that's fixed with the network size? And can we get rid of that threshold behavior so that we really can push it all the way to load factor to 1 without having that thing. So these were the question that we asked, and we felt if we really could do that, this would be quite nice. This would be really cool. Okay, so that was a bit the challenge that we have to. So that was if you know me a little bit, sometimes I say, oh, how hard can it be? Okay, this can't be too hard. There has to be a simple solution. Okay, and often it's not quite true. But I think you have to be sometimes be a little bit naive in order to have the courage to tackle a problem. Anyway, so we were very say, oh, it can't be that hard and things like that. And then actually, so let's see, so what's the problem? So first you have to understand what's really the problem. And something that you will, when you read the literature a little bit and think about it, you're going to see a little bit what's the cause of the problem. So here is the problem with CSMA. So it samples the schedule and the pink and the black schedule with the right probability, half in this and half in that. But the problem is, let's assume you're in the black schedule, or let's say all black nodes tend to transmit, and you are a pink node. So in order for you to have a chance to even make a transmission, all your four neighbors, all the black nodes, the four black nodes, they have to be silent. Okay. Now, if the attempt rate goes to infinity, whenever you sense it to be idle, you immediately start again. This is going to happen with a very, very low probability. Okay. So this is just locally that if your neighbors are active and all of them have to be inactive at the same time for you to have a chance to transmit. But once they stop talking, they immediately start again. It's very hard to jump in. Okay, and moreover, so that's kind of one. But also, in order for the pink schedule to take over, not only one pink node has to take over, but that has to happen all over the place. So because of this CSM tends to lock in. So it goes into the black schedule. It stays for a very, very long time in the black schedule. And then kind of by chance, it switches to the pink schedule. And once it's in the pink schedule, it stays for a very, very long time in the pink schedule. And the amount of time it stays in the pink schedule depends on the size of the network. Okay, and as the network becomes larger, it grows exponentially fast, how long you stand at that. So this is the problem. Okay, and if you read the literature, you realize that quite fast. Okay, and now it comes with the embarrassing thing. But it's I think, again, so then we said, okay, what can you do to get around that? And you see the problem is really, so you go into the black schedule, you stand a lot in the black schedule, the pink nodes cannot transmit, so they're going to see a terrible delay, okay? And so we said, I mean, the simplest thing to do is, what you do is you have to break up the schedule. So once you're in the black schedule, you cannot stay there and wait until by chance you go to the pink schedule, but somehow you have to disturb the black schedule. And the simplest thing would be to kind of, after some t time units, you just tell everybody to be silent and you start building the schedule again, okay? And when you do that, of course, you're not going to lock in, okay? Because every t time units, you're going to reset the thing and you start transmitting again, okay? Now, if you hear that, you say, okay, but this is really stupid, okay? It's stupid, it's not very elegant, it's stupid for one reason. I mean, okay, you have to unlock, you have to tell everybody to be silent. How would you do that? Okay, but you also feel this is not going to work. Because these t-time units, it should not be too large. It should be a couple of packet transmissions. So now when you reset and everybody is silent, you have to start to build a schedule again. And if you have a random schedule, your throughput is not going to be very high. So you would say when you always stop and stop and stop, your throughput is not going to be very high. Okay? And the question is really, if you do that, your delays may be going to be better, but how much throughput are you sacrificing? Okay, and maybe when you see it, you say this just looks so stupid. Let's not even think about it. For come and say, okay, let's as a starting point. Now, why don't we look into it? Just try to at least characterize this. And then it was actually quite interesting. Okay, so here are the results. So now the service rate depends both on set, how aggressive you are, but also T, how often you break up the schedule. Okay, so if the T is very small, you break it up all the time, so nobody would have that. So it depends on these two things. Okay.
Do you interrupt transmissions, or do you wait till they're all finished?
Oh, actually, right now you interrupt. You would interrupt. Yeah. But I mean, this is starting point. It's just say, okay, when this happens, what would happen? I mean, here it's. You see, you have to see where we were coming from. We were coming from a point where the delay grew exponentially in the network size. You say, is this really a fundamental limit, or is there a way to do something better? And this is really what this is about. But once you have that, then you can say, well, can you do better in terms of implementation on that? But we're not quite there yet. So this is the epsilon then, so it depends on the things. And the question is, as you choose t, what t do you need to use in order to get a given epsilon? Okay, so if t goes to infinity, you have the classical CSMA, so you know you can be throughput optimal. If t is very short, probably you cannot be throughput optimal. So the question is, as a function of t and z, what is you can do? And here the answer was that in order to get epsilon close to 0.5, okay, so 0.5 is the best you can do for any schedule. So in this part, this would be the throughput optimal. The t has to be 1 over epsilon to the power 2. Okay, so this trade-off does not depend on the network size. And that's something, I mean, if you see it for the first time and you have thought in that field, you say, oh, okay, this cannot be. Okay, something has to be wrong here. But this is something that it does not depend. So how fast you get to this capacity, only it's 1 over epsilon to the square. Okay, and so here is a little bit an example. So here are time units from 0 to 200. These are different network sizes. I think this is 10 by 10. Maybe 20 by 20, 40 by 40, and maybe a 50 by 50. Okay, and here you see how you start with a random schedule, or let's say everybody is silent, so you start with a throughput 0, and then you wait until you get something up to 0.5. Okay, and here you see over time how does your throughput grow, and when you see that the curve always looks the same, it looks a little bit like a square root. And it always looks the same. It does not be 10 to. The only thing that you see here is a little bit more noise. And if you have a larger network, it smooths out. So it starts to look like a mean field. Okay. But here it really kind of how fast you go to a tightly packed schedule. I mean, this here is really the interpretation. It does not depend on the network size. It's just it does not depend on the network size. Okay, and this is interesting. So the mixing time depends on the network size, but how fast you go to a tightly packed schedule, it does not depend on the network size. Okay, and because of that, you can now get a throughput delay trade-off over 1 over epsilon to the power of 3. That's for the grid and the torus. Yeah.
So it might depend on the network size to test something else.
Excuse me?
It might depend on the network size.
Yeah, of course. So right now it's a grid. And it's uniform, and it's a very simple case, but that's where we started. I would say, wow, this is interesting. Okay, so it does not, and before it was exponential. Now it's fixed, but it's also, I mean, there's 1 over epsilon, there's a 3 and not a 1. Okay, and so that's what we got. So the way to look at this is a little bit an existence result. There exists the interference graph and the situation where your delay performance is actually very, very good. Okay, this is maybe not the best. And I think that's also an open research question. I mean, could you get a throughput delay trade-off maybe with a different type of protocol? That's 1 over epsilon to the power 2, to the power 1.5. How close can you get to 1 over epsilon? Okay, so we haven't invested. It's one data point that you can get this. And this is, and it's much better than exponential in the network size growth. Okay, and so here is a illustration. So that's what we have with CSMA. And that's what we have with the new one, where we reset. And you see that now it looks much more great. So that you don't have this threshold behavior anymore, where it shoots up. And moreover, when you look at the different network sizes, I mean the delay curve, they look identical. Okay, the delay does not depend on the network. Okay, and if you have done research, let's say, on this topic. And you saw that result around 2012, you would have said, wow, this cannot be true. Okay, this is just too good to be true. Okay, but it shows that actually, at least in this situation, CSMA type of protocols, they can have a pretty good delay performance. Okay.
What's the size of T? I can't remember. It's very big with respect to packet time, or
no, it can't. I mean, here you see the average queue length. If you see the average queue length, say 100, you can get to 0.84 roughly, let's say 0.85. So these are 100 these are 100 packets kind of there. So I said
T was, for me, was the time where you do the
so it has to be a few at most a few packet transmissions.
Then what about the packets that don't get fully transmitted? They're resumed on the next?
They have to be resumed, yeah.
Of course, it's exponential. So
yeah.
What if you operated a slotted system? Wouldn't that work?
We haven't looked into that. I mean, we kind of wanted to have something very simple, so it has to be asynchronous.
Simple, I thought, no?
to analyze but not to implement, you don't need to have synchronization. So the idea here is really to have something that you can implement so you don't have synchronization. But that's a good point, okay? And I think there is also possibility, yeah, so it's a good point. I mean, maybe here now you could interrupt transmissions, and the question is, when you do that, how do you do that? How do you deal with this, okay, so that you don't lose the work that you already did?
But you have to deal with that now.
Yeah, I mean, right now this is a bit more theoretical, kind of what, yeah. But it's a good point, a very good point, yeah. I would have to go back how carefully we looked into this, yeah. And so this is, I mean, so this is, so here are some comments. So basically, it's at least at this time, it was a little bit a different perspective, that you went from a delay that grow exponentially, a delay that is fixed in the network size. Also, kind of from I mentioned that analysis, rather than a mixing time analysis, it's a time until you reach a tightly packed schedule. And this behavior is very, very different. Another thing is that the interference model matters. So this type of results, you won't get it for arbitrary interference graph. But our intuition, the fact that the interference are local is key. Okay. And also, right now, we said, okay, we kind of interrupt every T. So this could be done in a distributed manner. Okay, so right now we assume that there is, you really say now relog, now stop, but this could be done in a distributed fashion. Okay, so that's something that we had, and we felt this is quite exciting, but of course it's also restrictive. Everything was uniform, it was a grid and a torus. The question is now, if you have a more realistic situation, what's going to happen? Okay, so it should be a random topology. Let's say you have nodes are randomly distributed over the plane. You have non-uniform arrival rates, and maybe you also have some rate control. Okay, because if you have to make sure that you stay within the capacity region. So what would happen then? So here I just show two graphs. So this graph here is for the torus, where everything was agreed and idealized and what we got. This one here is now for a random topology where we use the utilities maximization framework to do rate control. Okay, and if you look, the core curve, they're really you see they're a little bit different, but also they're very, very similar. Okay, and the intuition is the results that you get here, they're really they carry over to the more general setting. Okay, and this is now the intriguing thing to do. Is can this be done? Can this also be shown analytically that this can be done in a more general setting? So that's a little bit the research challenge here. Okay. Now the question is a little bit how do you analyze this type of a system? And at least to me, it's quite intriguing. So here is so you have to look at the transient behavior of how these schedules evolve. Okay. So here's a picture over time. So here's a grid topology. And so it's not black and pink, but it's blue and red. Okay, so we have blue balls and red crosses. These are nodes that belong to different schedules. Okay, so whenever you see here you see regions where the red schedule is active, and you see regions where the blue schedule is active. And maybe this is after some time unit, you have some configuration of which schedules are active. Does that make sense? So here's just a snapshot, you reset the system, you wait a little bit, you take a snapshot, links of which schedule are active. And they have to be either black, they have to be blue, or whether it's an even or a odd node, it belongs to one or the other schedule. And here we indicate by color which one it is. Does that make sense?
They are not interfering? There is no interference?
No, there's no interference, no. So you see always between the red and the blue, where you have a boundary here, there has to be a little bit larger distance in order to have the separation. So yeah, so maybe it's a good point. Here things are very tightly packed, but whenever you go across a boundary, things are not that tightly packed. And that's where you lose throughput. Okay, so this is after a snapshot. And then you let the system. So after some time, it's going to look like this. After sometimes it's going to look like this, and you start to see that now the red schedule start to take over. Okay, and if you keep on going, at some point, almost everything is going to belong to the red schedule. Okay, so basically what you have here is a situation. Where two schedules compete with each other, and you have a random starting configuration, and then now they start to compete. Okay, and basically where they compete are on these boundaries here. Okay, they kind of try to push each other in and out. And so maybe here you see a little bit on this one here, how the shape changes over time. So it gets squeezed together. And in order to understand the performance, you really have to characterize the process of how these islands here, how they shrink with time. Okay.
Does it stay red for a long time after that? Is this just a typical trajectory?
So that's a very
the intermediate.
No. So that's the way to look at it is you start with a random. You wait a little bit, and here it just looks 50-50, red and blue. And then as you go on, as time goes on, one schedule starts to take over. And in this case, it's the red schedule. At some point, basically almost everything is going to be red. And once it's red, it's going to be red for a very, very long time. So this is just the transient. But what we show is that this phase here, to start with something that looks random, to get to something that's really dominated by red, this goes relatively fast. And so it's to describe this behavior. And then once you have all red, then it's very hard this area here, it's very hard for the blues to take over. And so this is the process that you have to analyze. And I think also the tools to do that, it's at least to me, they're not trivial, they're not that obvious, but I think it can be done. And it's kind of, at least to me, it's very intriguing. Okay, so let's see how I didn't put everybody to sleep. Okay, so here are the conclusions. So I think, maybe a take-home message is a little bit, there has been a lot of work in wireless networks. For a long time, people thought we can't really build these ad hoc wireless networks with high throughput and a low delay. And it provides a little bit a new perspective that maybe this can be done. You get good performance, but the protocol has to be a little bit different. So what we used here is a way to reset things. Another approach, and I think Sejong looked into that, is instead of having one channel to have multiple channels in parallel and to get around that. And maybe there are other ways to do it. But I think by now people know there is a way to get low delays. And this is a little bit the new perspective. The other thing, I think also the analysis of this type of protocols is quite different than what we had before. Also, the interference model, it matters. Okay, so right now here we have the interference graph. We looked at the grid. We looked at kind of a random geometric graph. Something else that we looked is at where you have primary interference constraints. So it's a little bit a different model. And there it actually looks even better. There it seems that if you have a very dense network, you actually get 1 over epsilon. So primary interference constraints seem to have very, very good properties in terms of throughput and the delay. And also feel there's still many, at least to me, many fascinating problems open, both in terms of the analysis, in terms of coming up with protocol ideas. And Jim mentioned, okay, we do things that somehow, okay, you get a result, but it doesn't, at least to me, it doesn't feel quite right. So can one do other things that are a little bit more intuitive, but also in terms of the analysis. And my feeling is that these problems can be solved, that in the end there's going to be indeed a very simple protocol that is going to perform very well. And when, let's say, maybe you're going to have it in a few years, and then 10 years, looking back, people are saying, why did it take them so long to figure out that protocol? Because it's so simple, it's so obvious. So that's a bit my intuition. Often in networking, if you think long enough and hard enough, you're going to find very simple solutions to problems that seem to be very, very difficult. And I think something, at least that's my hope that drives a little bit, something similar is going to happen here. And my feeling is also when this problem can be solved, the practical impact could be quite, could be considerable. I mean, there's a lot of talk about the Internet of Things and so on, and there you're going to have potentially a lot of nodes very densely together. Maybe each node has just a small transmission rate, but if you have many, many of them together, maybe still congestion becomes a problem. And these should be simple devices, very simple protocols. So how do you do that? So I think in order to really create the Internet of Things, there has to, I think at some point, this type of problems have to be solved. Yeah. So maybe I stop here, and if you have questions, I'm happy to answer them. Thank you very much. Yeah.
Go back on Jim's question, like the reset time capital T, you said it would be like a couple of packets.
Yeah.
But as you go to close to the boundary, like it should scale up. I mean, like if you're very close to the stability region, to the stability threshold,
Yeah.
you should like have a large T. It should go up, no? And you have this formula 1 over epsilon squared.
Yeah, that's what it is. Where was it again? Yeah, so that's how T has. So yeah. No, but yeah, your epsilon is 0.00001. Of course, your T is going to be large. And then you're going to take a large delay into account. But the point was here, I mean, that's what I meant. You want to have, in order to be practical, I mean, maybe you have to be here, maybe to have a queue of, let's say, maybe a few tens of packets. So you could go, if you believe that graph, you could go up to 0.8 to the capacity region. Okay. And you have the same thing in the MM1Q. I mean, if your arrival rate becomes very large, your delay is going to be quite high. So you have to find an operating point where you're happy. But here, the point is with the operating point, maybe you're going to be happy, is maybe going to be at 0.8, something like this. And this is maybe not too bad. It's better than, yeah, I think it's not too bad. I think maybe Jim knows more, but I think if you operate the network around 0.8, 0.9, that's more or less where that's not too bad, or not?
That would be typical, I guess.
Yeah. So this is the way we interpret it a little bit. With this type protocol, you potentially can operate it in a regime that seems to be typical. Let's say what you would do for a wired network. But of course, if you want to go all the way to 1, I mean, yeah, it's going to shoot up, and it's going to shoot up faster than 1 over epsilon. So you can, yeah. That's what I meant with T should not be too long. Yeah, so does that make sense? Yeah. Yeah.
So you mentioned the possibility result by stickies and others.
Yeah.
How far away are you from the possibility?
A lot. I mean, this is completely different. You see, I gave a talk where David C. was in the audience. And I started saying we're going to present a protocol that's fully distributed, that has low delay and a high throughput. And so David started to type on his computer, and he sent an email to another colleague and said, this guy doesn't know what he's talking about, because we just published a paper that showed that this cannot be done. Okay, so it's completely different. Basically, he said it cannot be done. It's just not possible. I mean, it said that basically the delay should have to increase exponentially. Okay, that was their result. But the catch is that their result is for general interference graph. The idea is I can construct a very weird interference graph where you cannot do that. And I think it's going to happen if you can interfere with nodes that are very, very far away, that you can get very strange patterns. But the point here is we have local interference. It should not happen. And I think people should have noted that before. I mean, in a wireless network, when I only interferes with my local neighbors, somehow the size of the network shouldn't matter for the delay that I see. It just seems very, very strange. I mean, let's say what this would say, if you really have a French-wide network, somehow what happens in Marseille influences your delay here, and somehow it seems, I mean, there's math behind it that says that could it be, but somehow it seems there should be a way to decouple these things a little bit. So on one hand, it's from, if you look at it historically, the results were quite surprising. I'm not sure how Seong, but when we presented them for the first time, people said this cannot be right. Okay, there has to be wrong. I mean, you go from exponential to bounded. That cannot be true. Okay, there has to be somewhere an error. There's something, that, yeah. But I mean, to the best of our abilities, I think, and also that's why we did the numerical results and all that. It really seems to be true, and I think now there are other groups that show that things like this really can be done. But it's fundamentally different, and I think that's the thing. It's a complete, I mean, it's exponential and bounded. I mean, there's a huge difference.
They've actually embarrassed about their paper, no?
Which one?
The Shah says this. I mean, if they made assumptions about the nature of the graph, which are just not realistic for the applications.
No, I would not go that far. It always depends what kind of result they want to show. Maybe what they show is that if you see a paper where they allow a kind of an arbitrary interference graph, it cannot be done. Okay.
The
If so,
interference graph doesn't make sense, as you said,
in a wireless, yeah.
So
But what is interesting here, maybe I'm not sure how interesting it is to the people in the room, but finding this max rate schedule, I think also in combinatorial optimization, it's like a fundamental problem. To a lot of it's not just in scheduling, but a lot of combinatorial optimization problems, you have to solve a very similar problem. And there you want to know, can you do it efficiently or not? So I think also the results that we have here, so I did not pursue that, but I think so I'm not sure, for example, David Marnik, I know at MIT is interested in these things, to find fast solutions for this combinatorial. And maybe the result is going to be similar. Okay, that's my speculation. If you look at optimization, you have linear optimization, you have convex optimization, where things go quite well. Maybe with this is something similar. So depending on the interference graph, you can find solutions quite fast, but maybe for arbitrary you cannot. So I think there is a connection there to be able to characterize for what type of interference graph you can solve combinatorial optimization problems efficiently. And I think there are some people interested in that field, and I think in this context, these things make a lot of sense. I think it always depends a bit on the context, yeah.
In your algorithm, how do you reset all the nodes in a distributed manner?
So that's something, so we had this result, we said you have to do it in distributed manner. How could you do it in principle, okay? And the simplest way, it's not the best way, but if you really want to do it, you would use busy tones. So you would, somebody starts the busy tone and then it gets propagated. And if you haven't gotten a busy tone within t time units, you would do it again. And as long as the propagation time of the busy tone is relatively short compared to a packet transmission, you're not going to lose too much. And we looked into that a little bit. So this would be one way to do, but it's not the most elegant way. So I think in terms of implementation, things we do are not the most elegant. And I think that also is an interesting question. What's a good protocol? It has good performance, but also has an elegant implementation. Yeah.
did you say what the U stands for?
Oh, for unlocking.
Unlucky.
Unlocking. No, it's not unlocking. Unlocking. Because you kind of, it locks into a schedule and you unlock the schedule. So that was, I'm not sure whether it's the best word, but kind of at some point we said we have to find something. So that's what we called it. Yeah. Great. Yeah.
More questions? So thank you.
Yeah, thank you very much.